Hey everyone, it's Mr. Fawcett, and we are about to start part 3 of our Limits at Infinity video. So in our last video, we talked about some rules that we could use for rational functions to figure out what the limits at infinity are, and also we just began to touch on the relationship between what the limits were equal to and what or where the horizontal asymptotes of that function are. So we're going to begin today by talking more specifically about that relationship and writing down what our calculus justification is for where a function has a horizontal asymptote. And I just went ahead and posted this definition, and now we can discuss. Y equals a is a horizontal asymptote of f of x if and only if the limit as x approaches infinity of f of x equals a, or the limit as x approaches negative infinity of f of x is equal to a. And note that a must be a real number. One thing that may concern you is that it says or. So why don't both of the limits at infinity have to equal a for it to be a horizontal asymptote? Well, the answer is we can actually have two horizontal asymptotes of a function. If the limit as x approaches infinity is equal to 10, and the limit as x approaches negative infinity is equal to 5, then we would have two horizontal asymptotes, one at y equals 5 and one at y equals 10. So again, as long as one of those limits is equal to a real number, that real number will be at one of the horizontal asymptotes. So we are going to use this justification in the problems below. Let's go there now and then talk about what the expectations are. So it says, use the concepts above to find the limits at plus or minus infinity. State where there are horizontal asymptotes, if any, and check your work by graphing on TI-84. So two things you need to do. Well, three if you're going to check your work on your calculator. But the first one is find the answer to the limits, and I would encourage you to go through the intermediate steps that we did in video 2. That'll show me that you really understand what's going on with those power rules for rational functions. And then 2, state where the horizontal asymptotes are, if there are any. If there's not, just say that there aren't any. All right, take some time to do that, and then come back here to the video, and we'll go through, actually we're going to go through all of them. Okay, hopefully you've had some time to work. We're going to start with number 5. And remember that we can break these functions down and create an approximate function that we can use to find the limit. One that's going to be easier to find the limit of than the initial one that we're given. So if I rewrite this function, we know that this function is approximately equal to the ratio of the two leading terms when x is very large. Right, so, and that works when x is either very large in the positive direction or very large in the negative direction. These two are not very good approximations, or the red one is not a very good approximation of the blue one when x is closer to 0. But when they're very large, the leading terms play a much more significant role than the other terms in the polynomials. Once we've come up with an approximate function, and there's no further way to simplify this red function, we can find the limit of the red function, which is going to be equal to the limit of the black function, the one that we started with. And we know that if the denominator has a higher power than our numerator, then the limit at infinity and the limit at negative infinity, although this question is just talking about the limit at infinity, is going to be equal to 0. But we can think through this, right? If we forget the rule, we can think through and say, okay, if I have a fraction 5 divided by 6x squared, 5 is always going to stay the same regardless of what x is. And if I keep dividing 5 by larger and larger numbers, right? Because if I substitute in 10 and then substitute in 100, the denominator is going to be larger when x is equal to 100 rather when x is equal to 10. That means that 5 is going to be split up into smaller and smaller pizzas, right? We thought about that pizza example. If we cut a pizza up into 10 slices, those slices are going to be bigger than if I cut it up into 1,000 slices, which are going to be bigger than if I cut it up into 100,000 slices. And eventually, as you increase the number of slices, the area of each slice is going to get closer and closer to 0, right? Because the slices are getting smaller and smaller and smaller. So that's why that specific power rule works. But it's good to know the why rather than just jump to the rule. So for the rest of these problems, I'm not going to do all of this intermediate work. I am just going to talk us through the different power rules for rational functions. That being said, I did encourage you at the start to write the intermediate steps for all of them because at this point we're solidifying our understanding, right? Further down the road, once we know this inside and out, we don't have to go through all the intermediate steps. But because this is one of the first times we're talking about this in the calculus class, I would encourage you to go through that work. All right, let's move on to number 6. So number 6, we are looking at the limit as a function approaches negative infinity. I'm going to take a look at these powers, and I'm going to notice that the denominator has a higher power than the numerator. So right away, I know that my limit at negative infinity is going to be equal to 0. Now, something we forgot to do for number 5, but we'll do it at the same time for 5 and 6, is we have to talk about where the horizontal asymptotes are, right? And we know from our justification up above that the answers to our limit expressions are going to be the values for where our horizontal asymptotes occur. So for number 6, we have a horizontal asymptote at y equals 0. And same thing for this function over here. There is a horizontal asymptote at y equals 0. All right, let's look at numbers 7 and 8. If I look at the two powers, the power of the numerator is 1, the power of the denominator is 1. So in this case, I look at the ratio of the coefficients, right? There's really a 1 in front of the x. So my ratio is 1 over 3, which means I have a horizontal asymptote at y equals 1/3. And again, if you did the intermediate steps, it may be easier to figure that out once you simplify and whatnot. You'll be able to simplify the function down to 1 over 3, the approximate function. But if we're just using the power rules, we can jump straight to what our limit's equal to. Number 8 is similar. Both powers are 2 for the numerator and denominator. So our ratio, or the answer to our limit as x approaches negative infinity, is 4/7. And we have a horizontal asymptote at y equals 4 over 7. Let's move on to our last two, 9 and 10. These are nice. If you remember the rules, these go by pretty quick. So number 9, the power in the numerator is larger than the power in the denominator. So we're not done yet. This is the two-part rule where we know that the limit's going to either be positive or negative infinity, but it's going to depend on the signs. So if I'm in this case, I'm going towards positive infinity. So if I substitute in larger and larger positive values, in my numerator, I'm going to get positive numbers because I'm squaring the numbers. They're always going to be positive. In my denominator, I'm multiplying the positive numbers by 2, which isn't going to change the sign. So my denominator is also going to be positive. So this limit is going to be positive infinity. Do I have a horizontal asymptote at positive infinity, right? Would it be correct to say horizontal asymptote at y equals infinity? Well, we couldn't place that on the graph, right? There's no place to put a horizontal line at infinity because infinity is not a number on the y-axis, right? Infinity is an idea. And that's why we said in our justification that the horizontal asymptotes will occur as long as the answer to the limit is a real number, right? We had that asterisk that said a had to be a real number. So if our answer to a limit expression is infinity, there will not be a horizontal asymptote. So this would be incorrect. So there's no horizontal asymptote for this function. Number 10, similar. The power in the numerator is greater than the power in the denominator. Now we just need to figure out whether this limit's going to positive infinity or negative infinity. I'm substituting in negative numbers because I'm approaching negative infinity. So my numerator, if I substitute in negative numbers to my numerator, right, and I cube them, if I cube a negative number, that's going to be negative. It's going to stay negative. And then if I multiply by 6, it's going to stay negative. In my denominator, if I square a negative number, that's going to become positive. And then if I multiply the positive number by 3, that's going to stay positive. So because my signs are different, this is going to approach negative infinity. And like the last problem, there are no horizontal asymptotes for this function. Okay, so if you're still struggling as to understanding the why these different power rules work, right? We have 3 of them that we talked about in either lesson 1 or 2. If you're not understanding the why, go back and rewatch these videos and then work through these problems again with all the intermediate parts. So try to write out those intermediate steps of creating a similar function that approximates the original and then finding the limit of that new function once it's simplified. It might be helpful to talk through it out loud, talking through why the numerator is approaching either a positive or a negative value, why the denominator is approaching a positive negative value, why, if the power in the denominator is larger than the power in the numerator, why the limit's going to be equal to 0. Again, just being able to explain these rules in your own words rather than just regurgitating the actual rule itself. So I look forward to seeing you in the next video. Until then, enjoy the rest of your day. This is Mr. Fawcett with another AP Calc AB lesson.